The nearest star sounds close on a map of the night sky, but in reality it lies across a gulf so vast that every machine humans have ever built still falls painfully short. Between Earth and that faint red star stands a chain of limits: speed, fuel, radiation, isolation, time, and the fragile biology of the human body itself. This journey into the true scale of space reveals why the first star beyond the Sun remains far beyond human reach. Please like the video, subscribe to the channel, and settle in for the full story. Seen from Earth, the night sky appears crowded. Stars seem scattered across a shallow dark ceiling, near enough to belong to the same surface. Constellations hold their shapes so steadily that the eye accepts them as fixed patterns. Orion rises with the same belt, and the bright points of winter and summer return in order. Human sight receives this arrangement as a map of nearness. It offers no natural sense of depth. A bright star may seem close because it shines strongly. A faint star may seem distant because it barely glows. In reality, brightness and distance are only loosely tied, and the sky hides its structure efficiently. What appears compact from the ground is spread across an enormous three-dimensional volume. The solar system occupies only a minute pocket within that volume. Around the Sun move the planets, dwarf planets, moons, comets, asteroids, dust, and streams of particles. Even this familiar system is already far larger than daily intuition can hold. The Earth circles the Sun at a distance of about 150 million kilometers. Neptune moves roughly 30 times farther from the Sun than Earth does. The Kuiper belt extends beyond Neptune, and long-period comets may come from a much more distant reservoir around the Sun. Yet all of this, even when stretched to its coldest remote edges, remains local. It belongs to one star and its small family of orbiting matter. Beyond that family, the wider stellar neighborhood begins. In that neighborhood, the Sun is not exceptional in location. It occupies an ordinary part of the Milky Way, within a region that contains other stars separated by distances so large that ordinary travel loses meaning. The nearest known star system is Alpha Centauri, a group of 3 stars. 2 of them, Alpha Centauri A and Alpha Centauri B, circle one another. A third, the faint red dwarf Proxima Centauri, lies somewhat farther from that pair and is the closest known star to the Sun. Red dwarf means a small, cool star, dimmer than the Sun and much less radiant. To the eye from Earth, Proxima does not dominate the sky. It is close by stellar standards, yet human sight alone does not grant it any special importance. Its distance gives it that importance. Proxima Centauri lies about 4 1/4 light-years away. A light-year is the distance light travels in 1 year. Light moves through empty space at about 300,000 kilometers each second. So a single light-year is a measure of length, and it is vast beyond habit of thought. 4 1/4 light-years means that even light, the fastest thing known in nature, takes more than 4 years to go from that star to Earth. When Proxima is seen in the night sky, its light begins the journey years earlier. The star is never seen as it is in the present instant. It is seen as it was when that light left its surface and started crossing the dark between stars. This fact begins to restore the real scale of the local cosmos. Within the solar system, light needs only a little more than 8 minutes to travel from the Sun to Earth. It reaches Neptune in a matter of hours. These are large spans when compared with the speed of aircraft or the motions of the ground. Yet they still feel connected to one living frame of time. 4 1/4 years is different. That span belongs to memory, weather, illness, recovery, childhood, and age. It is a human interval, and light itself must spend all of it crossing only the first step toward another star. The nearby sky contains other stars as well, some bright, some inconspicuous, each placed at its own distance and moving with its own velocity through the galaxy. Barnard's star is close by. So is Wolf 359. Sirius appears brilliant in part because it is relatively near, though still much farther than any planet. These stars do not sit like pins on a fixed dome. They move slowly through space, and over long periods the shapes of constellations change. Human lifetimes are usually too brief to notice this directly without careful measurement. So the sky seems stable while it is in fact drifting. The stillness is an effect of scale. Distances are so large that motion hides itself inside time. Astronomy learns that depth by measurement. A nearby star shifts position slightly against more distant stars as Earth moves from one side of its orbit to the other. This tiny change is called parallax. Parallax gives the first rung of the cosmic distance ladder, the set of methods used to measure greater and greater reaches of space. The shift is minute even for the nearest stars, which itself reveals the size of the surrounding gulf. If a star only 4 1/4 light years away barely seems to move when Earth travels from one side of its orbit to the other, then the space outside the solar system is already operating on a scale far beyond ordinary spatial sense. From the ground, the difference between the solar system and the nearest star can be easily misunderstood because both are placed under one name, space. Yet these are different orders of emptiness. Distances inside the solar system, immense as they are, remain part of one gravitational household centered on the Sun. Distances between stars belong to the wider architecture of the galaxy. A journey to Mars crosses planetary space. A journey to Proxima Centauri leaves the Sun's immediate family and attempts a crossing measured not in months or even years of ordinary travel, but in the language of stellar separation itself. This is why the nearest star is already enough to humble every instinct shaped on Earth. Human beings evolve among hills, rivers, coastlines, forests, and weather. Even their largest machines are built around scales that fit within a single world. The mind can imagine a voyage across an ocean or around a planet because those are distances that still belong to a shared horizon. The gap to Proxima Centauri does not belong to that kind of experience. It is close only when stars are compared with other stars. It is near only on a galactic map. For a human traveller beginning from Earth, the nearest star is not a nearby destination waiting just beyond the edge of effort. It is the first clear sign that the universe, even in its local form, is built on distances that resist the body, the machine, and the lifetime alike. Beyond the last familiar outline of the solar system, space does not open into a crowded frontier, it opens into absence. The imagination often fills that absence with structure, as if the way from one star to another must contain hidden stations, drifting worlds, bright clouds, or some visible road across the dark. In reality, the region between nearby stars is defined first by how little it contains. It is not empty in the strictest scientific sense, but to human senses and to ordinary material life, it is close to empty beyond anything found on Earth. The path outward leaves behind the visual richness of planets, rings, moons, and sunlit dust, and enters a realm where almost nothing happens in any local, immediate way. The night sky as seen from Earth encourages a false compactness. Countless stars lie overhead at once, and their simultaneous visibility makes them seem gathered into one common space. Yet between the Sun and the nearest star stretches a gulf so wide that both systems remain almost entirely alone within it. If the Sun were reduced in thought to a small luminous sphere, and placed at one end of a long plain, Proxima Centauri would not appear just beyond a hill. It would stand so far away that the plain itself would cease to feel like one connected setting. The middle region would dominate the arrangement. The stars at either end would become less important than the vacancy between them. That vacancy has no horizon. On Earth, every landscape offers some boundary of experience. Mountains close a valley. Water meets the line of the sky. Even a desert presents a ground beneath the feet and an atmosphere above the head. Interstellar space offers none of this. There is no natural up or down, no floor, no weather, no nearby reference point by which motion can be judged. A spacecraft leaving the Sun's neighborhood would not pass through a sequence of visible districts. It would move through darkness so uniform that location would have to be known by calculation rather than by direct sensation. The region itself does not announce where one is. Darkness there also differs from ordinary night. A night on Earth is never truly black. Air scatters light. The ground reflects it. The moon, cities, clouds, and the glow of the atmosphere soften the dark. Even a remote desert sky is rich with starlight. Between stars, the darkness is more complete because local sources of illumination are almost absent. The sun, once distant enough, dwindles into an unusually bright star among other stars. Its warming presence fades. Its glare no longer defines the scene. Light still exists, arriving from many remote objects, but it is thin, scattered, and weak. Space is not a black wall. It is a vast dimness with points of light suspended across it, each one too far away to change the emptiness around the traveller. This gives the region a strange visual character. The stars remain visible because they are luminous, but their light does not fill the surrounding volume. A bright point does not make the emptiness around it seem inhabited. The nearest stars would continue to look like stars rather than growing quickly into large suns. Their apparent size would change only very slowly across enormous spans of travel. For much of the journey, the outward view would remain deceptively familiar. The destination would still resemble a point in the distance. The origin would also shrink into one more point behind. A traveller moving across interstellar space would therefore experience little of the dramatic visual transformation expected from ordinary travel across Earth, where landmarks enlarge steadily and the destination announces approach. Cold is another defining feature, though even cold must be described carefully. Temperature in empty space is not felt in the same way it is felt in air or water. There is almost no matter present to carry heat into skin or metal through contact. Yet the region between stars is still profoundly cold, because there is so little energy available locally. Away from strong sunlight, matter loses heat by radiation and receives very little in return. The background glow of the universe remains, but it is faint. Interstellar space is therefore a place where warmth is not supplied by the environment. Any warmth that remains around a human-made object must be generated and preserved by that object itself. Silence, too, belongs to this region, though silence in space is more than quiet. Sound requires a medium such as air, water, or solid material through which vibrations can travel. In the near vacuum between stars, sound does not spread from place to place in the ordinary way. A ship may vibrate internally, machinery may hum through its own structure and atmosphere, but outside, the gulf stays without audible expression. No storm moves through it, no wind crosses it, no wave breaks upon it. The space between stars offers no surrounding soundscape to reassure the body that it remains inside a shared environment. It is a setting without voice. Because so little changes from one place to the next, time begins to dominate perception. On Earth, distance is often felt through changing scenery. In interstellar space, distance would be felt through duration. The emptiness itself gives few cues of progress, so the calendar becomes more meaningful than the window. Days, months, and years would mark movement more clearly than sight would. This is one reason the gulf between stars feels unnatural to human imagination. It is not only large, it withholds the ordinary signs by which large journeys are understood. It offers no forest thinning into plains, no coastline nearing at sunset, no mountain range rising ahead. It gives only separation extended across time. For this reason, the space between nearby stars is not simply the background of an interstellar voyage. It is the central fact of that voyage. The stars at either end are important, but the condition to be crossed is the interval itself. It is thin, dark, cold, trackless, and nearly featureless. It contains too little to support life and too little to guide intuition. It turns the nearest star from a visible neighbour into a destination divided from Earth by a region that is vast in a way human movement has never been designed to endure. Before any engine is chosen, before any ship is built, before any biological limit is measured, that region states the problem. The nearest star is not blocked by a wall or by a boundary. It is kept distant by the character of the space in between. The space between stars appears empty from far away, yet it is not truly blank. It contains a scattered substance so thin that ordinary experience has no direct comparison for it. Astronomy gives this substance a name once, the interstellar medium, meaning the matter that lies in the regions between stars. After that brief definition, its nature is simpler to describe in plain terms. It is a sparse mixture of atoms, ions, molecules, dust grains, magnetic fields, and high-energy particles spread across enormous distances. In 1 cubic centimetre of Earth's air, there are countless particles packed together. In much of the space between nearby stars, there may be only a few particles in that same volume, and in some regions even fewer. This is not emptiness in the absolute sense. It is matter thinned almost beyond imagination. Because it is so diffuse, this material does not resemble fog, cloud, or smoke in any human way. A person does not move through it and see swirls crossing a beam of light. It does not form a visible curtain hanging between the sun and the next star. Most of it would pass unnoticed by the eye. Yet thinness alone does not mean irrelevance. Spread across a distance of more than 4 light years, even a tiny average density becomes a real environment. The journey to another star does not pass through nothing. It passes through a medium so rarefied that it seems harmless at first thought, but so persistent that its effects grow with distance and speed. Much of this matter is hydrogen, the simplest and most abundant element in the universe. Some of it is neutral, meaning its atom keeps its electron. Some of it is ionized, meaning the electron has been removed, leaving a charged particle. There is also helium and smaller amounts of heavier elements, along with dust grains made of materials containing carbon, silicon, oxygen, iron, and other common cosmic ingredients. These grains are tiny, often smaller than the width of a human hair by many orders of magnitude. Yet they remain real pieces of matter drifting between stars. In some colder regions of the galaxy, molecules can form, including simple compounds such as molecular hydrogen and carbon monoxide. In the local region around the Sun, the gas is especially thin, but it is still there, and the Sun itself moves through it. This material is not spread evenly. Space between stars contains warmer and cooler patches, thinner and slightly denser areas, and regions shaped by old supernova explosions, stellar winds, and magnetic fields. The Sun sits inside a local zone sometimes described as a cloud of very thin interstellar gas. Even that name, cloud, can mislead if taken too literally. It does not mean a visible puff with distinct edges as seen in Earth's sky. Its boundaries are broad and its density is extremely low. Yet the term survives because, on galactic scales, these regions do have differing properties and can be mapped by their temperature, composition, and motion. Light reveals this sparse matter in indirect ways. Starlight passing through dust is dimmed and reddened because shorter wavelengths are scattered more effectively than longer ones. Radio telescopes detect hydrogen by its characteristic emission. Spectra, the spread of light into its component colours, show which atoms lie along a line of sight. Astronomers therefore know that the dark between stars contains structure, even when human eyes perceive only blackness. The local stellar neighbourhood is not a clean void separating one system sharply from another. It is a shared galactic environment, thin and tenuous but physically present. For human travel, what matters is not only that this material exists, but that motion changes its significance. A spacecraft moving slowly through such a region encounters little immediate force from the surrounding gas. The particles are too few and too widely spaced to resemble atmospheric drag on Earth. A craft drifting gently through interstellar space would not feel wind pressing against its hull in any ordinary sense. But the meaning of a collision depends on relative speed. A single grain of dust at walking speed is trivial. The same grain at a substantial fraction of the speed of light carries enormous energy. The environment does not need to be dense to become dangerous. It only needs the traveller to move through it fast enough. This is one of the quiet traps hidden in the idea of a fast journey to another star. Great distance encourages a desire for great speed. Great speed transforms the medium from near emptiness into a field of impacts. Each hydrogen atom, each helium nucleus, each microscopic grain becomes a projectile because the ship supplies the relative motion. The danger is not that interstellar space is crowded. The danger is that even a very sparse environment cannot be ignored when the journey demands extreme velocity. The medium remains patient. It fills the route continuously, particle by particle, over trillions upon trillions of kilometres. There is also no natural clearing in which a ship can simply leave matter behind. The local interstellar environment extends in every direction. One path may be slightly thinner than another, but no route becomes truly free of gas and dust. The galaxy contains matter on every scale, from thin local plasma to dense molecular clouds, and even the clearer regions still contain a background of particles. A ship bound for the nearest star must therefore accept that it travels through a real material setting from departure until arrival. The problem is not solved by better aim, or by choosing a cleaner lane across the dark. The dark itself contains substance. This substance also carries charge and magnetism. Charged particles respond to magnetic fields, and magnetic fields thread the interstellar environment on large scales. These are not fields that a person could see hanging in space like lines in a diagram, but they influence the motion of plasma, the hot gas made of charged particles. The result is a medium that is not only sparse but active in subtle ways. It flows, shifts, compresses, and interacts with stars and their outflows. The Sun does not stand apart from this. It moves through the galaxy, and the boundary of its own influence adjusts in response to the surrounding material. So the region between the Sun and the nearest star is not simply a length to be measured, it is a physical medium to be crossed. It is thin beyond ordinary understanding, yet not negligible. It is dark, yet traceable by its effect on light. It is quiet, yet filled with particles in motion. It is almost empty, yet not empty enough to grant safe passage at the speeds interstellar travel would require. In this way, the interstellar medium changes the meaning of the journey. The gulf between stars is not a passive blank. It is a sparse but real ocean of matter, and over such enormous distance, even an ocean this thin begins to resist. The sun does not end where its light grows faint. Its domain reaches far beyond the planets in a form that cannot be seen directly by ordinary eyes. From the sun flows a continuous outward stream of charged particles, mainly electrons and protons, called the solar wind. This flow carries energy and magnetic field with it. Near Earth. It is already part D reminds human technology that the sun is not only a source of light and heat, but also a source of moving plasma, hot gas whose atoms have been stripped into charged particles. Far beyond Earth, this outward flow continues to expand into the dark, and in doing so it creates the largest single structure belonging to the sun. That structure is the heliosphere, the vast bubble carved into surrounding galactic space by the solar wind and the sun's magnetic influence. It is not a shell of solid matter. It is a changing region in which solar material still dominates over the surrounding interstellar environment. All the planets orbit inside it. Even the most distant known dwarf planets remain deep within its interior. In this sense, the solar system is not only a family of bodies circling the sun, it is also a much larger occupied region, one defined by the outward reach of the sun's particles and fields. To leave the sun in the deeper physical sense, a spacecraft must leave this bubble behind. The heliosphere is not fixed or perfectly shaped. The solar wind changes with the sun's activity, and the surrounding interstellar gas and magnetic field press back. As a result, the boundary region breathes, shifts, and responds over time. Its exact shape remains a matter of study. Some models give it a long tail, somewhat like a comet. Other models suggest a more compact and distorted form. What remains clear is that it is not a neat sphere drawn with uniform radius in all directions. It is a living boundary between one star's influence and the wider conditions of the galaxy. For a long stretch outward from the sun, the solar wind races way faster than waves can travel through the plasma around it. In that state, physicists describe the flow as supersonic. The word does not refer to sound in the ordinary earthly sense of air carrying noise to an ear. It refers more generally to a flow moving faster than the characteristic wave speed in that medium. As the solar wind expands, it thins. Over immense distance, it loses the ability to push outward unchanged against the material beyond the sun's bubble. Somewhere far past the orbit of Pluto, the flow is forced to slow abruptly. That region is called the termination shock. A shock in this context is a sudden change in the properties of a flowing medium, including speed, density, temperature, and pressure. At the termination shock, the solar wind ceases to race outward in its earlier state. It slows from supersonic to subsonic flow. The change does not create a wall in the human sense. A spacecraft does not strike a barrier like a cliff face in darkness. It passes through a region where the character of the solar wind alters sharply. Plasma becomes denser and more turbulent. The orderly outward rush becomes more compressed and disturbed. The sun is still present there in influence, but its outward stream is no longer moving with the same freedom. Beyond the termination shock lies the heliosheath, the broad outer layer of the heliosphere. Here the solar wind has slowed, heated, and become more chaotic. It continues outward, but not in the clean, strong form it had closer to the sun. This is a zone of mixing pressure, bending fields, and competing flows. It is still part of the sun's realm, Yet it is no longer the calm interior of the heliosphere. It is the frontier layer, where the sun's extended atmosphere meets resistance from the galaxy outside. The farther outward one goes through this region, the more the balance changes, solar influence weakens, external pressure matters more. At the far side of the Helios heath stands the heliopause. This is the outer boundary of the heliosphere, the place where the solar wind is no longer strong enough to hold the surrounding interstellar medium back. It is not a hard surface, but it is a real division. Inside it, the plasma is dominated by the solar wind. Outside it, the local interstellar medium takes over. Magnetic fields, particle populations, and plasma properties change. A spacecraft crossing it does not leave the solar system in the sense of abandoning the sun's gravity altogether, because the sun's gravity extends endlessly outward, weakening with distance. But it does leave the sun's protective bubble. It passes from solar space into interstellar space. That protective role matters. The heliosphere helps reduce the number of galactic cosmic rays reaching the inner solar system. Cosmic rays are high-energy particles that move through the galaxy and can damage electronics and living tissue. The heliosphere does not block them entirely, yet it acts as a partial shield. As a result, the boundary of the sun's domain is not only a geometric edge, it is also a change in exposure. A craft crossing outward begins to leave behind part of the protection supplied by the sun's extended magnetic environment. Humanity has not crossed this region often. Only the 2 Voyager spacecraft have passed through the heliopause and entered interstellar space. Voyager 1 does so in August of the year 2012. Voyager 2 follows in November of the year 2018. Their crossings show that the boundary is not identical in every direction, and that the outer heliosphere is complex rather than simple. These spacecraft do not carry people, and they move slowly by interstellar standards. Yet even they require decades to reach and pass this outer edge of the sun's influence. Their achievement quietly reveals how large the sun's domain truly is. Before any journey to another star even begins in earnest, the traveller must first spend years escaping the invisible bubble of the star already left behind. So the way from Earth to the nearest star does not begin at the edge of Earth's atmosphere, nor even at the orbit of the last planet. It begins with the long outward crossing of the heliosphere itself. The sun fills a vast region with wind, particles, and magnetism. Its frontier is diffuse, shifting, and physically real. To leave the familiar space of one star and enter the shared environment between stars, a craft must move through the slowing solar wind, across the disturbed breadth of the Helios heath, and beyond the heliopause into the wider galactic medium. Only there does the outward journey truly leave the sun's domain behind. Distance by itself is only part of the problem. Human beings do not travel through distance alone, they travel through time. The nearest star remains 4¼ light-years away, which means even light, moving at about 300,000 kilometers each second, needs more than 4 years to cross the gap. That fact already sets the scale. If the fastest thing known in nature requires years, then any vehicle far slower than light enters a different regime entirely. One measured not in voyages but in portions of a lifetime, in generations, or in spans longer than recorded history. Inside the solar system, long travel still fits inside human expectation. A mission to the moon takes days. A mission to Mars takes months. A mission to the outer planets takes years. But the word years still belongs to one coherent human story. A child can understand it. A crew can train for it. Engineers can build around it. Interstellar distance breaks that pattern. The gap to Proxima Centauri is not merely farther than Mars or Jupiter. It is so much farther that the unit of thought must change. The mind cannot simply extend ordinary mission planning outward and expect the same logic to survive. This becomes clearer when known spacecraft speeds are placed beside the distance. Voyager 1, the farthest human-made object from Earth, moves at about 17 kilometers each second relative to the Sun. New Horizons leaves Earth faster than any previous spacecraft launch, at about 58,500 kilometers per hour. These speeds are remarkable within the history of spaceflight. They are enough to cross the orbit of planets, enough to leave the heliosphere over time, and enough to make the solar system feel traversable by machines. Yet when they are compared with the distance to the nearest star, their greatness begins to shrink. At Voyager 1's speed, a simple crossing of 4¼ light years would take about 75,000 years. At the launch speed of New Horizons, the same journey would take about 78,000 years. These are not mission lengths in any normal human sense. They are longer than agriculture, longer than cities, longer than writing, longer than most surviving monuments. A spacecraft could be launched under one civilization and arrive under another so changed that continuity might not even remain. The trip would not merely outlast a crew, it would outlast nations, languages, institutions, and almost every stable human framework ever known. This is why interstellar travel immediately becomes a problem of extreme speed. To bring the journey into a span resembling a human career or a single lifetime, the vehicle must move not a little faster than present spacecraft, but vastly faster. A craft moving at 1% of the speed of light would still need about 424 years to cross 4¼ light years. A craft moving at 10% of the speed of light would still need about 42 years, and that estimate ignores the time required to speed up and slow down. These are not small improvements over present capability. They require a leap from kilometers each second into a significant fraction of light speed. That leap is difficult to grasp because everyday movement teaches the wrong lesson. On Earth, increasing speed often feels like a matter of stronger engines, better fuel, or better design. A faster aircraft remains an aircraft. A faster ship remains a ship. But interstellar travel does not ask for a modest extension of known flight. It asks for motion on a scale that approaches the deepest speed limit built into nature. Every order of increase becomes harder than the last. The difference between a spacecraft moving at a few tens of kilometers each second and one moving at a significant fraction of the speed of light is not the difference between a slow train and a fast train. It is the difference between ordinary engineering and a regime where energy demands become overwhelming. Time also changes the meaning of the destination. A trip that lasts decades may still preserve a living relationship between departure and arrival. A trip that lasts centuries begins to break that relationship. The world left behind changes beyond recognition. The people who planned the mission die. The institutions that financed it may vanish. The culture that launched the craft becomes history to those still traveling, if any are still traveling at all. A journey lasting tens of thousands of years no longer connects two nearby moments in civilization. It becomes closer to geological patience than to exploration. In that sense, speed is not simply a convenience. It is the difference between a voyage and an abandonment. Communication suffers the same scale. Even if a craft could move outward successfully, messages remain bound by the speed of light. A signal from Proxima Centauri takes more than 4 years to return to Earth, and a reply takes more than 4 years to go back. The simplest exchange stretches across nearly a decade. Human operations in space have so far depended on delay measured in seconds, minutes, or at most many hours. Interstellar distance forces delay into years. This means that the mission is not only physically remote, it becomes temporally remote, detached from direct guidance and from the shared rhythm that joins mission control to spacecraft today. So the speed required for a trip to the nearest star is not defined by ambition alone. It is defined by what kind of mission still counts as humanly meaningful. At present speeds, the answer is stark. Known spacecraft do move outward, but they do so on timescales that turn the nearest star into a destination beyond any individual life, and beyond most forms of social continuity. To make the crossing plausible for humans, a vehicle must reach velocities far beyond those achieved by ordinary rockets. It must do so safely, reliably, and with enough control to arrive rather than merely pass through darkness. The distance to the nearest star therefore does more than set a far target. It declares that interstellar travel begins only where present spaceflight, in temporal terms, has barely begun at all. Once the sun's outer domain has been left behind and the time required for the crossing has been faced plainly, the next barrier appears in the form of the engine itself. A journey to the nearest star does not fail first because there is no destination. It fails because no propulsion system now available to humans can drive a crude spacecraft to the necessary speed. Propulsion means the method by which a vehicle pushes itself forward. In space, that usually means throwing mass backward so that the craft moves forward, or using light or electromagnetic force in a more indirect way. The central difficulty is simple to state and hard to solve. The nearest star is so far away that a practical journey demands extraordinary speed. Yet every known path to great speed runs into severe physical limits. Chemical rockets are the foundation of spaceflight. They are powerful, direct, and proven. They burn fuel and oxidizer, create very hot gas, and force that gas through a nozzle to generate thrust. Thrust is the push that moves the vehicle. Chemical engines provide strong thrust, which is why they're so useful for launch and for major maneuvers in space. They can lift spacecraft away from Earth, send probes to the planets, and shape complex missions across the solar system. But they do this by expelling reaction mass at speeds that are still far too low for interstellar travel. Chemical propulsion is excellent for escaping Earth and navigating the Sun's planetary system. It is not enough for making the gulf to another star short enough for human life. The limitation is not a small matter of engineering refinement. It comes from the nature of the method itself. Chemical reactions release energy by rearranging electrons in atoms. That is enough to produce powerful explosions and useful rocket exhaust. But it is modest when compared with deeper energy sources inside atomic nuclei. A chemical rocket can become more efficient through better design, lighter structure, improved fuels, or clever staging, yet it remains a chemical rocket. Its exhaust speed rises only within a limited range. That means the spacecraft's final speed also remains limited. For travel inside the solar system, that may be acceptable. For travel across light years, it is not. Electric propulsion offers a different path. Instead of producing a short, forceful burst of hot gas, it uses electrical power to accelerate charged particles to much higher exhaust speeds. Ion engines are a well-known example. They use electricity to push particles out of the engine very efficiently. Efficiency here means that less propellant is needed for a given change in speed. That makes electric propulsion extremely valuable for many deep space missions. A spacecraft can run such an engine for months or years and gradually build up a large total change in velocity. This is a genuine advance over ordinary chemical rockets for some purposes, yet the trade is severe. Electric propulsion usually produces very low thrust. It pushes gently, almost delicately, and depends on long operating time. That is useful for robotic missions. It is far less helpful for launching a heavy crewed interstellar vessel toward a significant fraction of the speed of light. This creates a painful split in current propulsion. Chemical systems give strong push but poor long-range efficiency. Electric systems give high efficiency but weak push. One kind is forceful and wasteful. The other is economical and gentle. A starship for humans would need both very high overall performance and the ability to move a large mass in a meaningful amount of time. Present propulsion methods do not unite those strengths. They divide them. Nuclear propulsion is often placed one step beyond this divide. In nuclear thermal propulsion, a reactor heats a propellant and expels it through a nozzle. Because nuclear energy is more concentrated than chemical energy, this can provide both strong thrust and better efficiency than ordinary rockets. Nuclear electric propulsion uses a reactor to generate electricity, which then powers electric thrusters. These ideas are serious and actively studied because they could improve human travel to Mars and to the outer planets. They may shorten travel times within the solar system, but even here the scale of the star problem remains. A method that is a major improvement for Mars is still nowhere near enough for a practical crewed trip to Proxima Centauri. Nuclear propulsion may be a bridge to better interplanetary travel, yet it does not close the interstellar gap. Solar sails and laser-driven sails reveal another way to think about propulsion. A sail does not rely on throwing large amounts of propellant backward. Instead, it uses the pressure of light itself. Sunlight can push on a reflective surface, and a very large, very light sail can slowly gain speed without consuming onboard propellant. This is elegant and real. Small demonstrations have shown that sunlight can indeed move a spacecraft. Laser-driven concepts extend the idea by using intense beams to push a tiny sail much faster than sunlight alone can manage. These concepts are among the few known approaches that point toward truly high interstellar speeds. Yet they do so by moving very small payloads, not human crews. A gram-scale probe is one thing, a shielded human habitat, with machinery, supplies, structure, and reliability, is another. The physics does not forbid sails, but the scaling from tiny chip-sized probes to living starships is immense. Fusion propulsion appears often in serious interstellar studies because fusion releases far more energy than chemistry and, in principle, could support far higher exhaust speeds. Fusion is the process that powers stars, where light atomic nuclei combine and release energy. On paper, a fusion engine seems closer to the kind of power interstellar travel demands. But paper is not flight. Controlled fusion remains difficult even for stationary facilities on Earth, and a working fusion power plant on Earth is not the same thing as a compact, dependable fusion engine in a spacecraft. A crewed starship would need such a system to start reliably, run safely, survive for years, and direct its energy into thrust with extraordinary control. No human-built machine does that today. So the propulsion barrier is not the absence of ideas. Human thought produces many ideas. It is the absence of a working engine that combines enough energy, enough control, enough reliability, and enough scale for a human crossing between stars. Every present option solves only part of the problem. Chemical rockets are mature but too limited. Electric engines are efficient but too weak. Nuclear systems are promising but aimed mainly at the solar system. Sails avoid some burdens but favor tiny payloads. Fusion remains an aspiration rather than an operational tool. The journey to the nearest star therefore stops at a fundamental point. It does not yet stop at the destination. It stops at the engine room, where no available propulsion method can presently turn human intention into a practical interstellar departure. An engine alone does not carry a spacecraft to another star. it must push something, and that something has mass. The deeper this fact is followed, the more severe the problem becomes. A starship must carry structure, engines, guidance systems, power systems, communications equipment, thermal control, shielding, supplies, and, if humans are aboard, a complete living environment. If the craft uses onboard propellant, then it must also carry the reaction mass that the engine throws backward to move forward. This turns propulsion into a burden that grows upon itself. The ship must carry fuel to move the ship, but part of that ship is the fuel itself. The more fuel it carries, the more fuel it needs to push that fuel. This compounding burden is one of the oldest truths in astronautics. A rocket does not simply add propellant in the way a ground vehicle adds petrol to a tank. A ground vehicle can carry more fuel and accept a manageable penalty in weight because it is supported by wheels or by water, and because its engine does not need to throw large fractions of its own mass backward at extreme speed. A rocket operates differently. It must accelerate everything it still has not yet burned. At the start of the journey, the engine struggles against the full mass of the loaded craft. Only as propellant is expelled does the vehicle become lighter. That means the early part of the burn is always paying to move a future exhaust supply as well as the useful payload. Payload means the part of the spacecraft that actually matters for the mission outcome. In a simple robotic probe, the payload may be instruments, communication systems, and onboard computers. In a human starship, the payload is far more demanding. It includes people, habitat volume, air, water, food systems, medical capability, waste processing, protection, repair equipment, and a structure strong enough to survive for decades or longer. The crew cannot be reduced to a tiny package in the way a sensor can. Human presence imposes a minimum scale, and every kilogram of minimum human need becomes part of the mass that the propulsion system must handle. This leads to a hard asymmetry between robotic and crewed travel. A robotic craft can be small, stripped down, and built around narrow scientific purpose. It may accept risk, silence, and one-way operation. A human vessel cannot. It must sustain bodies and minds continuously. It must remain habitable after failures. It must include redundancy, meaning important systems are duplicated so that one breakdown does not end the mission. Redundancy is safety, but safety is mass. Repair capability is survival, but survival is mass. Comfort may be reduced, yet there remains a floor below which a human mission becomes no longer humane or no longer viable. That floor is heavy. The fuel burden also multiplies because the starship does not merely need to leave Earth. In the broad physical sense, it must accelerate to very high speed, survive a long crossing, and perhaps slow down at the far end if arrival is to mean more than a fast flyby through another stellar system. Slowing down is especially costly. A spacecraft that only accelerates in one direction may cross the gulf quickly, but it reaches the destination moving so fast that it cannot remain there in any meaningful way. To enter orbit around another star or to approach a planet carefully, the craft must remove much of its speed. If it carries the propellant needed for both acceleration and deceleration, the initial mass grows even larger. The ship departs not only with the burden of the outbound crossing, but with the burden of a future braking system already on board. This is why mass ratios become so punishing. A mass ratio compares the fully loaded spacecraft with the mass left after propellant is spent. A modest ratio may be manageable. A large ratio can dominate the design. For interstellar ambitions using familiar propulsion concepts, The required ratios can become so extreme that the useful payload shrinks toward insignificance beneath mountains of propellant. The ship begins to resemble a fuel delivery system, whose purpose is to deliver more fuel to a later stage, which then exists to deliver still more fuel to a later phase. The actual crew habitat can become a tiny surviving fraction of the total launch mass. In such cases, the architecture loses practical meaning. Staging can reduce some of this burden. A multi-stage rocket throws away empty tanks and engines that are no longer needed, allowing later stages to avoid carrying dead mass. This is one reason staging is so effective in launch vehicles. Yet staging does not solve the interstellar problem cleanly. It helps by discarding parts, but each stage must still be built, fueled, guided, and integrated into the whole mission. For a crewed starship, staging across deep space adds complexity, failure points, and design difficulty. It is also far less helpful once the mission demands both large habitat mass and a means of slowing down at the destination. Refueling along the way might seem like relief, but the path between stars does not provide convenient depots. The interstellar medium is far too thin to collect economically with known technology, especially at the enormous rates a fast-crewed craft would require. A mission might in principle send fuel ahead, build infrastructure over centuries, or rely on external beams or support systems. But these are no longer simple spacecraft solutions. They become civilization-scale engineering programs. The burden of fuel has not vanished. It has only been moved outward into a larger network of prior effort. Every kilogram added for one reason also calls forth other kilograms. More propellant requires larger tanks. Larger tanks require more structure. More structure requires more thrust. More thrust may require larger engines. Larger engines generate more waste heat and place greater stress on the craft. Greater stress may demand thicker supports and stronger materials. If the payload is human, added mission duration requires more supplies and more system reliability, which again add mass. The design therefore grows in linked chains. The burden is not additive alone, it is recursive. Each solution deepens the demand for another solution. This is why fuel is not merely one engineering concern among many. It sits near the center of the interstellar problem, because it reaches into every other part of the spacecraft. The tyranny lies in the fact that mass does not stay where it is assigned. It spreads its consequences throughout the whole mission. A starship must carry what it needs, and what it needs to move often becomes larger than what it exists to protect. So the nearest star remains not only a question of distance and engine power, but of load. The ship grows heavy with its own means of travel, until the journey threatens to disappear beneath the mass required to make the journey at all. After the burden of mass comes a quieter burden that hides inside every powerful machine. A starship does not only need enough energy to move, it must also survive the heat produced while that energy is used. On Earth, heat often feels manageable because air and water carry it away. Wind cools metal. Flowing liquid removes warmth from engines. Even a hot machine usually stands in an environment that helps accept some of its waste. Deep space behaves differently. It is cold, but it is not a cold bath. It offers almost no material in direct contact with the spacecraft. A ship cannot dump its excess heat into surrounding air, because there is no surrounding air. It must radiate heat away as infrared light, and that is a slower process. This changes the meaning of power. Power is the rate at which energy is used or transferred. A starship capable of interstellar travel would require immense power, whether that power came from chemical reactions, nuclear systems, external beams, or some more advanced source. To accelerate a large human vehicle to extraordinary speed, the engine would have to channel energy on a scale far beyond ordinary spacecraft. Yet no engine is perfect. Some part of the energy becomes the desired motion of exhaust or vehicle. Another part remains behind as waste heat inside chambers, pipes, magnets, electronics, structures, and living spaces. The greater the total power, the greater the thermal burden. This is not a small engineering detail hidden beneath the main design. It is a central physical limit. A machine may in principle produce enormous power, but if it cannot get rid of the unwanted heat, that power becomes self-destructive. Components expand, soften, crack, warp, or fail. Electrical systems drift out of tolerance. Sensors lose accuracy. Delicate materials age quickly. Human beings also add to the problem, because a crewed vessel is not only an engineer of the payload, it is a habitat full of bodies and equipment that must remain within a narrow temperature range. A human ship cannot simply allow its interior to swing between freezing darkness and furnace-like overload. Rockets already reveal this problem in a limited way. During launch from Earth, engines operate at extreme temperature and pressure, but they do so briefly, and the vehicle is not required to maintain that performance continuously for years. Tanks are emptied, stages are discarded, and the hardest thermal moments pass. An interstellar vehicle is different. If it aims to build up tremendous speed over long periods, it may need to run major systems for months and years. In such a craft, thermal management becomes part of propulsion itself. The question is no longer only whether the engine can make thrust. It is whether the whole ship can survive the waste energy created while making that thrust. Even a very efficient propulsion method does not escape this difficulty. Efficiency means that a larger share of input energy becomes useful motion rather than unwanted heating. But unless efficiency is perfect, some share still becomes heat. And at interstellar energy scales, even a small imperfect fraction may be enormous. A system that wastes only a little percentage of a gigantic power flow may still produce enough heat to destroy an unprepared spacecraft. In the vacuum of space, the main way to remove heat is through radiators. A radiator is a surface designed to glow heat outward. The hotter it is, the more rapidly it can radiate, but materials can survive only up to certain temperatures. If the designer keeps the radiator cooler, then the area must grow very large. This creates another severe trade. Large radiators add mass, which deepens the propulsion problem already faced. They also add structural complexity. They may need pumps, pipes, working fluids, panels, joints, and protection against damage. What begins as a thermal requirement soon spreads into architecture. The ship does not merely need an engine and a habitat. It needs broad artificial surfaces whose purpose is to shed the heat that the rest of the ship cannot endure. The problem grows sharper when energy is stored or processed on board. A nuclear reactor may provide tremendous endurance, but the reactor itself produces heat that must be managed whether the ship is accelerating or not. Power conversion systems also warm up. Electronics that route current or control plasma can become thermal bottlenecks. If the mission relies on intense onboard lasers, particle beams, or electromagnetic systems, those devices also lose some fraction of energy as heat. Nothing powerful remains thermally neutral. The ship becomes a balance between energy gained for motion and energy rejected for survival. There is also a cruel mismatch between acceleration and cooling. To shorten the trip meaningfully, the craft wants high power. High power means rapid heat generation, but radiative cooling depends on surface area and temperature, not on the urgency of the mission. The radiator does not care that the crew desires a shorter travel time. It removes heat only at the rate physics allows. This means that thermal control can set a ceiling on usable power. The engine may be capable of more, the fuel source may be capable of more, but the ship as a whole may be unable to tolerate more because it cannot stay cool enough. Heat therefore enters the interstellar problem at the level of the whole vehicle. It shapes engine choice, ship geometry, material selection, crew safety, and mission profile. It may force long periods of lower thrust simply to keep temperatures under control. It may require deployable radiators so large that the craft becomes fragile. It may favour some power sources over others, not because they are more energetic, but because their waste can be managed more gently. In this way, the thermal burden is not only about temperature, it is about how fast a human vessel can afford to be powerful. So a trip to the nearest star is blocked not only by distance, fuel, and engine design, but by a subtler law of balance. Every powerful act of propulsion leaves behind a residue of heat. In ordinary machines, that residue can often be tolerated or expelled into the surrounding world. In deep space, the spacecraft must carry the means of rejecting its own fever. The faster and more ambitious the journey becomes, the harder that fever is to control. A practical human starship would therefore need not only an extraordinary engine, but an equally extraordinary capacity to stay cool while using it. Without that, the energy intended to drive the voyage outward accumulates inside the vehicle and turns motion itself into a threat. In ordinary life, dust is a minor thing. It settles on surfaces, drifts in sunlight, gathers in corners, and is brushed away. Even sand, though abrasive, remains manageable when touched at low speed. The body learns from daily experience that small particles usually carry small danger. Interstellar travel breaks that lesson. In the space between stars, the particles are indeed small and sparse, but a fast spacecraft changes their meaning. At extreme velocity, size matters less than relative speed. A grain too small to notice in the hand can strike with the force of an explosion when the closing speed becomes high enough. The route to another star is therefore not only long, it is filled with countless possible impacts. The interstellar medium contains atoms, ions, and microscopic dust grains. Most of that material is spread very thinly, yet a ship travelling quickly does not meet it all at once. It meets it continuously, second after second, over years of motion. The faster the ship moves, the more material it sweeps through in a given time. This does not create atmospheric drag in the familiar sense, because the density remains far too low for that. Instead, it creates repeated collisions. Some are with single atoms and are individually small. Some are with larger grains and are much more serious. The danger lies in accumulation for the smallest particles and in sudden damage for the larger ones. The essential physics is simple. Kinetic energy is the energy of motion. When speed rises, the destructive potential of an impact rises very rapidly. A tiny particle moving slowly may tap a surface and do almost nothing. The same particle at a substantial fraction of the speed of light does not behave like ordinary dust. It behaves more like a concentrated burst of energy. On impact, both the particle and a portion of the struck surface can vaporize into hot plasma. A crater can form. Shock can spread through nearby material. Protective layers can erode. Sensitive instruments can fail. A collision too small to be seen before impact can still leave behind severe local damage. This changes the character of the ship's front face. The leading surfaces of an interstellar craft do not merely meet emptiness. They meet a stream of high-speed impacts created by the craft's own motion. Every part exposed forward becomes part of a shield, whether designed as one or not. Windows, sensors, antennas, radiator edges, and structural seams all become vulnerable. A design that works well in ordinary deep space near the planets may fail under such exposure because interplanetary missions do not normally face decades of impact at extreme velocity through the interstellar medium. The smallest particles create a slow stripping effect. One atom or one tiny grain does almost nothing by itself, but trillions of such impacts over time can wear down coatings, roughen surfaces, and degrade materials. A polished leading edge becomes pitted. A reflective layer becomes dull. A thin membrane may weaken. The problem resembles erosion, though not by wind or water. It is erosion by a sparse but relentless stream of matter met at very high speed. For a long voyage, even gradual wear matters because the ship must survive not for hours or months, but for many years without ordinary maintenance from outside support. Larger grains are worse because they concentrate damage into brief events. A microscopic grain may already be dangerous at high speed. A grain closer to the size of sand becomes a profound threat. It does not need to be common to matter. It only needs to exist somewhere along the route. Even a low probability becomes meaningful when a ship crosses trillions of kilometers. A single impact of the wrong size in the wrong place could penetrate layers, sever crucial systems, or shower the surrounding structure with secondary fragments. The problem is therefore statistical as well as mechanical. The craft does not merely need to survive the average environment. It must survive the rare but consequential encounter. This makes navigation harder than it first appears. Space between stars cannot be swept clean. There is no practical way to remove the dust along the entire route before departure. Telescopes can reveal many large objects, but they cannot map every tiny grain scattered across light years of darkness. The starship therefore travels through partial ignorance. It can estimate the environment from astronomical observations and from models of local interstellar conditions, yet it cannot know the position of each hazard in advance. Protection must be built into the vehicle itself. The ship must be able to accept that some impacts are unavoidable. One obvious answer is thicker shielding. A thicker front barrier can absorb more damage, spread shock, and protect the vital interior. But thickness adds mass, and mass returns immediately to the propulsion problem. A human starship already struggles under the burden of fuel, habitat, life support, and radiation protection. If its forward shield must also be made massive enough to survive years of bombardment, the launch mass grows further. This is why dust danger is not an isolated issue. It reaches back into engine design and mission feasibility. Protection is possible in principle, but every layer paid for in safety is paid for again in acceleration cost. Some designs imagine sacrificial shields, meaning outer layers intended to be damaged and gradually consumed while deeper layers remain intact. This is a sensible concept, and versions of it are already used in spacecraft protection against micrometeoroids. A thin outer layer can break up an incoming particle and spread its energy before it reaches the main hull. Yet interstellar speeds raise the severity far beyond ordinary orbital conditions. The shield may need great standoff distance, multiple layers, and substantial depth. It may also need active systems, such as forward detection, plasma deflection, or clouds of material released ahead of the craft to intercept incoming grains first. Such ideas are serious, but each one adds complexity, mass, energy demand, or uncertainty. For a robotic probe, some of these risks may be accepted. A tiny fast probe may survive long enough to send back data even if it arrives damaged. A crewed vessel cannot accept that margin of injury. Humans require a ship whose critical systems remain reliable after years of cumulative impact. The craft must preserve pressure, temperature control, radiation protection, navigation, communication, and the integrity of the living habitat. A single major forward strike is therefore not just a technical event. It is a direct threat to human survival. So the dust between stars carries a deep lesson. Interstellar space is sparse, but not sparse enough to become harmless when crossed at extraordinary speed. The faster the ship travels, the more violent each small encounter becomes. The journey to the nearest star therefore runs into a hard contradiction. To make the trip short enough for human life, the craft wants extreme velocity. Yet extreme velocity turns ordinary dust and gas into a field of impacts that can tear, heat, erode, and puncture. In that way, the route itself fights back. The particles are tiny, the space is dark, and the distances are vast. But once speed rises high enough, the smallest matter in the void becomes one of the most serious obstacles on the way to another star. Beyond the sun's outer protective bubble, the voyage grows more exposed. Space is dark and thin, yet it is not gentle. It contains streams of energetic particles that move through the galaxy with enormous speed and carry the power to alter matter at very small scales. On Earth, living bodies develop beneath layers of protection so constant that they are easy to forget. The atmosphere absorbs much of the harmful radiation that comes from space. The magnetic field deflects many charged particles before they can reach the ground. Even in orbit around Earth, astronauts remain far closer to these protections than any crew on a journey to another star. Deep interstellar travel removes that shelter and leaves the spacecraft in a region where invisible exposure becomes a daily condition. Radiation in this setting does not mean warmth or light in the ordinary sense. It means energy carried by particles or waves. For deep space travel, the most serious concern comes from energetic particles. Some are protons, some are electrons, and some are atomic nuclei heavier than hydrogen, stripped of their electrons and moving at extreme speed. A portion of this radiation comes from the sun. Solar eruptions can accelerate particles and send them outward through the solar system. Another portion comes from much farther away, from violent events across the galaxy such as supernova explosions and other high-energy processes. These long-travelling particles are commonly called cosmic rays. They are not rays in the narrow visual sense. They are mostly matter in motion, arriving from space with remarkable energy. Near Earth, this danger is softened by distance, field, and atmosphere. Earth's magnetic field bends the paths of many charged particles. The atmosphere then acts as a deep blanket of matter above the surface. Particles striking it lose energy, break apart, or trigger cascades that are much less severe by the time they reach the ground. Human beings therefore live beneath constant protection without needing to think about it. Even at high altitude and in orbit, radiation exposure rises, yet it remains within a broader protective environment. A crew going outward through the solar system begins to lose part of that safety, and a crew moving beyond the heliosphere loses more. The heliosphere, though not perfect, serves as a partial shield against some galactic radiation. The solar wind and the sun's magnetic field influence how many energetic particles reach the inner regions of the solar system. Outside that bubble, the surrounding galactic environment becomes more direct. The ship enters a region where the local balance has shifted. The sun's protection has thinned behind it. What remains is a long crossing through a particle environment shaped less by one familiar star and more by the wider Milky Way. This exposure is dangerous because energetic particles do not need to arrive in large visible quantities to cause harm. One high-energy particle can pass through living tissue and break chemical bonds along its path. It can damage DNA, the molecule that stores biological instructions inside cells. It can alter proteins, disrupt normal repair processes, and create changes that the body may fail to correct. Some damage is repaired, some is not. Over time, unrepaired damage can raise the risk of cancer, contribute to degenerative disease, or harm tissues that do not easily renew themselves. The danger is therefore cumulative. It is not only a matter of surviving one burst, it is a matter of enduring a background of injury over long duration. The nervous system is especially concerning because some forms of radiation can reach deep into the body and affect delicate cells. The eyes are vulnerable as well. The blood-forming tissues are sensitive. Reproductive cells may also be harmed. In the short term, a sufficiently intense storm of energetic particles can cause radiation sickness, a condition in which the body's rapidly dividing cells are injured so severely that nausea, weakness, and more serious symptoms can follow. In the long term, even lower but persistent exposure matters because an interstellar voyage does not last days or months alone. It extends the time available for damage to accumulate. Not all space radiation is alike. Solar particle events can rise sharply and then fade. They are irregular and may be tied to eruptions from the Sun. Galactic cosmic rays are steadier and harder to escape because they arrive from all directions and include very energetic heavy nuclei. A heavy nucleus moving at great speed can do disproportionate damage because it deposits energy densely along its path. This means the deep space radiation problem is not simply about how much arrives, but about what kind arrives and how that energy is delivered into matter. A rare, highly energetic event may matter greatly, even in a generally sparse environment. Matter inside the spacecraft does not end the problem automatically. When energetic particles strike the hull or interior materials, they can generate secondary radiation. In other words, the incoming particle may collide with atoms in the spacecraft and produce new particles that continue inward. The ship itself can therefore become part of the radiation environment. This is one reason deep space exposure is harder to understand than standing in sunlight or avoiding a known source on Earth. The danger comes not only from outside, but from the interactions triggered when outside particles meet the material world carried with the crew. Electronics also suffer. Computer memory, sensors, control systems, and power equipment can all be disrupted by energetic particles. A single particle may flip a stored bit, confuse a detector, or degrade a component over time. In a short mission, this may be manageable through careful design and limited duration. In a mission lasting many years, the repeated arrival of radiation becomes a reliability problem as well as a medical one. A human crew depends on machines for air, water, temperature control, communication, navigation, and repair. Radiation therefore threatens not only bodies directly, but the artificial environment those bodies require. What makes deep space radiation especially serious for interstellar travel is the combination of distance and duration. Many hazards in space are dangerous because they are intense. Radiation is dangerous because it is both intense in certain events and persistent across the whole route. The journey does not pass through one brief hazardous zone and then return to safety. It moves for years through an environment in which exposure remains part of daily existence. The nearest star may be only the first step to the wider galaxy, yet even that first step asks human biology to remain healthy while immersed in invisible particle traffic far from Earth's natural protection. So the crossing between stars is not merely cold and empty. It is active at a microscopic level. Charged particles move through it from the Sun, from ancient stellar explosions, and from other energetic events across the Milky Way. They pass unseen through the dark, carrying enough energy to injure cells, disrupt machines, and slowly erode the biological margin on which human life depends. A crewed starship would therefore not travel through silence alone. It would travel through constant exposure, where the absence of air and weather conceals a different and deeper hostility. In that region, nothing needs to touch the skin or shake the hull to do harm. The danger enters at the scale of atoms and continues for as long as the voyage lasts. A human starship cannot rely on distance alone to keep its crew alive. It must carry protection with it, and that protection becomes part of the spacecraft itself. Shielding is the general name for material or design used to reduce harm from impacts and radiation. On a short mission near Earth, shielding can remain limited because the journey stays relatively brief, and because Earth's atmosphere and magnetic field still stand nearby in the larger environment. A voyage to the nearer star changes that balance completely. Protection is no longer an added feature placed around a vehicle that briefly enters danger. Protection becomes one of the defining purposes of the vehicle from the beginning. The need begins with simple exposure. Space between stars offers no natural wall against radiation, no atmospheric blanket, and no magnetic cocoon strong enough to be taken for granted. It also contains dust and gas that become more dangerous as velocity rises. The ship must therefore defend against more than one kind of threat at once. It must soften the steady arrival of energetic particles, endure the rare arrival of more dangerous bursts, and survive the forward bombardment produced by high-speed travel through thin matter. Each of these demands encourages thicker or more specialized shielding. Together they press the spacecraft toward heaviness. Material seems at first like an easy answer. If one layer is not enough, another can be added. If a wall is too thin, it can be made thicker. This works in principle, but mass grows quickly. Every added plate, every buried water tank, every structural rib, and every sacrificial outer layer must be accelerated for years and perhaps slowed again at the far end. Protection is never free. A stronger hull requires more propulsion. More propulsion often requires more fuel. More fuel requires more structure. The shield meant to preserve the crew thus reaches backward into the entire architecture of the mission. Radiation shielding reveals this especially clearly. Different materials behave differently when struck by energetic particles. Dense materials can stop some forms of radiation effectively, but when hit by very energetic cosmic particles, they may also produce secondary particles that continue inward. Lighter materials rich in hydrogen often help because they can reduce some kinds of radiation with less production of damaging secondary cascades. Water is valuable in this sense. So are certain plastics and other hydrogen-rich substances. This means the most useful protective mass may not always be the heaviest metal. A starship might place water, fuel, food stores, or waste processing reservoirs around living quarters so that ordinary mission supplies serve as part of the shield. This is an elegant idea, yet it does not remove the burden. It only gives 1 kilogram more than one job. The living space at the center of the ship would likely need a specially protected refuge for times of intense solar activity, a storm shelter, in the broad sense of the term. Such a space could be surrounded by water tanks, provisions, or dedicated shielding so that the crew spends dangerous periods inside a region of higher protection. This strategy may help with sudden radiation events, but it does not fully solve the slow pressure of galactic cosmic rays, which arrive over long duration from many directions and are difficult to block completely without very large mass. The ship may reduce the danger, but reducing is not the same as removing. Protection becomes a matter of degree, and degree is purchased with weight. Impact shielding imposes a second demand. The front of the spacecraft must survive the high-speed encounter with gas atoms and dust grains. One thick wall may not be the best answer. A more effective design may use multiple layers spaced apart so that an incoming particle breaks up at the outer surface and spreads its energy before reaching the inner hull. Such shielding already exists in more modest form for spacecraft threatened by micrometeoroids. But interstellar travel asks for a far harsher version. Layers may need to be deep, separated, replaceable, or supported by additional systems. The forward shield can begin to resemble a dedicated structure attached to the ship, rather than a simple thickened nose. This creates a difficult contrast inside the spacecraft. The crew benefits from openness, reliable access, and maintainable systems. The shield benefits from thickness, separation, and distance between outer and inner layers. The design therefore pulls in opposite directions. A compact ship is easier to support thermally and structurally, yet a compact ship leaves less room to arrange protective layers intelligently. A broad vehicle may create space for better shielding geometry, yet a broad vehicle presents more area to the incoming flow and may demand more material overall. There is no perfect shape that removes the trade. The need for shielding alters not only the mass of the vessel but also its proportions. Active protection is sometimes imagined as a substitute for thick material walls. Magnetic or electric fields might deflect charged particles, and forward detection systems might identify larger incoming grains. These concepts are serious enough to study, especially for radiation control, because fields can in principle act without requiring all protection to be passive bulk mass. Yet such systems demand energy, equipment, reliability, and precision. They also do not handle every threat equally well. Neutral particles are not easily turned aside by fields. Dust grains may carry little charge or arrive too unpredictably. An active shield may help, but it becomes another major system to build. Power, repair, and trust for years. The promise of lower mass is countered by the cost of greater complexity. The crew's own arrangement inside the ship also becomes part of shielding logic. Beds, work areas, medical spaces, storage, and water systems would likely be organized so that the most protected region lies deepest within the vehicle. In this sense, the ship begins to resemble a small fortress with layered defense rather than a simple vessel. The closer one moves toward the center, the greater the safety sought. But a fortress in space must still be accelerated like any other mass. It must still reject heat, maintain life support, and communicate across light years. The protective shell cannot be designed in isolation because it presses on every neighboring system. This is why shielding becomes weight in a deeper sense than mere mass on a scale. It becomes mission weight, conceptual weight, and design weight. The ship grows not only heavier but more burdened with interdependence. Water intended for drinking doubles as radiation protection. Structural members meant to hold tanks steady must also survive impact shock. Outer layers meant to catch dust may cast thermal shadows on radiators. Protected interior volume may shrink as walls thicken. Every answer disturbs some other part of the craft. So a crewed starship cannot simply be made safe by wrapping it in enough material. Safety has to be carried intelligently, distributed carefully, and paid for everywhere else in the mission. The deeper the shielding becomes, the more the spacecraft turns into an armored habitat whose protection is inseparable from its mass, and mass remains the enemy of speed. For that reason, the effort to defend humans from radiation and impact does not sit beside the propulsion problem as a separate challenge. It folds directly into it. The better the ship is protected, the harder it becomes to move. The easier it is to move, the less margin of protection it may be able to carry. Between those two demands, the dream of a human journey to the nearest star grows heavier, with every layer meant to keep the crew alive. A crewed starship cannot remain only a machine of motion and protection. It must also become a place of continued living. Once the journey to the nearest star is measured in many years or longer, the interior of the vessel takes on a new identity. It is no longer simply a cabin carried through space. It becomes a closed habitat, an artificial environment that must supply nearly everything the crew needs while cut off from Earth. Closed in this sense does not mean perfectly sealed forever without loss or exchange. It means that the ship must recover, reuse, and preserve its essential materials so effectively that outside resupply is no longer part of the mission. Air, water, food, cleanliness, and waste handling all have to be sustained inside a moving structure surrounded by emptiness. This requirement changes the scale of the problem again. A short mission can survive by carrying stores and accepting some waste. A long mission cannot depend on that pattern alone. If a crew simply consumes supplies and throws away what remains, then the mass of the mission rises rapidly beyond practicality. Water is heavy, food is heavy, spare filters, containers, and disposable equipment are heavy. Even oxygen, though invisible, becomes a significant mass when counted over long time. A human starship therefore has to behave less like a vehicle on a trip and more like a small world trying to keep its internal balance. Air is the first part of that balance. Humans breathe in oxygen and breathe out carbon dioxide. In a sealed habitat, carbon dioxide cannot simply be allowed to rise. At high levels it becomes harmful, causing headache, confusion, and more serious physiological danger. The ship must therefore remove it continuously. That removal can be done through chemical scrubbers or more regenerative systems that capture carbon dioxide and process it further. At the same time, the habitat must replace the oxygen that breathing consumes. A short mission can rely on stored tanks and replaceable cartridges. A long mission benefits from systems that regenerate part of the air supply by chemical means, perhaps using water as a source of oxygen through electrolysis. The process of splitting water with electricity into hydrogen and oxygen. What matters is not the specific device alone, but the principle of constant renewal. The atmosphere inside the ship has to be maintained every hour, quietly and without failure. Water stands beside air as a second foundation. The crew needs it for drinking, hygiene, food preparation, medical use, and perhaps cooling or shielding functions elsewhere in the spacecraft. Carrying all water for a very long interstellar crossing as a one-way supply would place a crushing burden on mass. The habitat must therefore reclaim water from breath, sweat, urine, washing, and other sources. Condensation captured from cabin air becomes valuable. Wastewater becomes a resource rather than something to discard. Each litre recovered is a litre that does not need to be launched from Earth. Yet recovery has to be reliable and clean. Water recycling is not merely filtration in the household sense. It must remove contaminants thoroughly enough that the same small stock can circulate again and again through human use without slowly becoming unsafe. Food deepens the challenge because it is not only a material input but also a biological need with complexity. Packaged food can last for years if carefully prepared and stored. Yet a very long mission cannot depend on packaged stores alone without devoting enormous mass and volume to them. Food also carries problems of nutrition, variety, decay, and psychological strain. A crew fed for years on a narrow range of preserved meals may remain technically alive while becoming increasingly burdened by deficiency, monotony, or storage loss. For this reason, long-duration habitat concepts often consider some level of food production on board. Plants may contribute fresh matter, oxygen recycling, humidity control, and a rhythm of cultivation that feels more lifelike than sealed containers alone. But plants are not simple solutions. They need water, light, nutrients, growing area, and careful control. A greenhouse in space becomes another life support system with its own points of failure. Waste closes the loop because every output from the human body and from daily living must go somewhere. In a disposable civilization on Earth, waste can be moved outward into larger systems. It can be buried, burned, diluted, treated, or carried away through natural cycles at planetary scale. A starship has no such outward world available. Waste left unmanaged becomes contamination, illness, smell, corrosion, and loss of useful material. The habitat must therefore process solid waste, wastewater, food residues, and expired materials with the logic of recovery. Some matter can be sterilized, separated, dried, or chemically converted. Some may return to agricultural use if food production exists on board. Some must be stored safely if it cannot be reused. In every case, the ship cannot think like a place with an outside. It has to treat its own waste as part of its continuing inventory. This turns life support into a network rather than a set of separate machines. Air recovery depends on power and water. Water recovery depends on plumbing, filtration, storage, and clean surfaces. Food systems depend on water, nutrients, temperature control, and perhaps lighting. Waste processing affects hygiene and air quality. A failure in one branch can spread into others. If water recovery weakens, hygiene suffers and food production may fall. If air chemistry drifts, crew performance declines. If contamination spreads through the habitat, the entire living system becomes less secure. Redundancy therefore matters here as much as in propulsion or shielding. A human habitat cannot rely on a single filter, one pump, or one processing line when the journey has no resupply and no rescue nearby. The ship must also keep its interior physically livable. Pressure must remain stable. Temperature and humidity must stay within narrow ranges. Surfaces must resist microbial growth. Lighting must be controlled in a way that supports sleep, work, and biological rhythm. Noise from machinery must remain limited because a habitat is not only a set of life functions, it is the entire sensory world available to the crew. The artificial environment has to remain orderly enough that people can continue to eat, wash, breathe, rest, and perform routine tasks year after year without the habitat itself becoming a source of constant decline. So the crewed starship becomes more than a vessel crossing darkness. It becomes a closed house of chemistry, plumbing, biology, storage, and maintenance. It must circulate its own breath, reclaim its own water, transform its own waste, and preserve or grow its own food. Every leak, impurity, and inefficiency matters because the habitat cannot depend on Earth once the voyage truly begins. In this way, the human problem of reaching another star is not only one of engines and shields, it is also the problem of carrying a small living world inside metal and asking that world to remain balanced, clean, fertile, and breathable while isolated in deep space for the length of the crossing. A journey to the nearest star does not remain only a matter of engines and life support once its duration extends beyond ordinary human schedules. Time changes the meaning of the crew itself. A mission measured in decades places strain on careers, families, institutions, and memory. A mission measured in centuries changes category altogether. It no longer asks whether people can survive a long expedition in the usual sense. It asks whether a human society can remain coherent while living inside a spacecraft for longer than the lives of the people who begin the voyage. At that point, the ship is not simply carrying travelers, it is carrying succession. Succession means one set of people handing a condition of life to the next. On Earth, this happens within civilizations, towns, households, and professions. Children inherit language, customs, practical knowledge, and social roles from older generations. Institutions preserve records and routines so that no single lifetime must hold everything alone. A long interstellar mission would need the same continuity, but compressed into a far smaller and more fragile setting. The ship would have limited space, limited population, limited resources, and no wider society beyond its walls. Every transfer of knowledge would matter more because there would be no outside culture to refill what had been lost. This makes education a central engineering requirement, even though it is not usually described in mechanical language. A crewed starship lasting beyond one generation would need children to grow into adults who understand the vessel that keeps them alive. They would need to learn navigation, maintenance, agriculture or food systems if such systems exist, medicine, repair, and social responsibility. They would also need history, not only in the broad cultural sense but in the specific sense of knowing why the ship exists, what its destination means, and how their present conditions arise from decisions made before their birth. If that chain weakens, the mission can drift. The technical structure may remain intact for a time, but the shared purpose holding people to it may fade. Purpose matters because a starship is not a neutral place to live. It is a designed environment with rules created for survival. Air and water cannot be wasted freely. Space cannot be used without restraint. Maintenance cannot be postponed indefinitely. On Earth, individuals can often neglect larger systems because society is wide enough to absorb many local failures. In a closed habitat, private habit and public survival are tightly linked. The way one person stores tools, handles waste, follows repair procedure, or responds to rationing can affect everyone. This means social discipline becomes part of life support. Cooperation is not merely admirable, it is necessary. Governance therefore enters the ship as more than politics in the familiar civic sense. Governance is the way decisions are made, rules are enforced, conflicts are settled, and authority is transferred. A long mission would need some durable form of governance that is accepted as legitimate by people born long after launch. This is a profound challenge. The first crew may consent to the mission willingly, understanding its hardship and accepting its structure. Their descendants would not have made that initial choice. They would inherit it. A society born aboard the vessel may come to regard the ship as home rather than as transport. The destination may feel abstract, distant, or even irrelevant compared with immediate daily life. In such a setting, authority cannot rely forever on the will of the founders. It must remain believable and workable for those who never saw Earth. Population also becomes a social variable rather than just a biological one. A very small population may struggle with genetic diversity, labor distribution, social stability, and resilience after accidents. A larger population offers more skills and more redundancy in roles, yet it requires more living volume, more food, more water, and more complex governance. The ship therefore cannot choose its population size freely. It must balance biological health, social variety, work demands, and material constraint. Every additional person brings both strength and burden. Too few people, and the society becomes brittle. Too many, and the habitat may exceed its carrying capacity, the maximum population the closed system can support without decline. daily life would matter as much as formal structure. Human societies are not held together only by laws or technical manuals. They are held together by ritual, routine, expectation, and shared meaning. Meals at known times, educational cycles, work rotation, maintenance schedules, celebrations, mourning practices, and common stories all help a group remain stable. In a starship cut off from landscapes, seasons, and ordinary historical change, these patterns may become even more important. They provide rhythm where the external environment provides almost none. Through repetition, the society would mark time and preserve order inside a setting where the view outside changes only slowly across years. Language and culture would also evolve. No human group remains unchanged across generations. Pronunciation shifts, vocabulary narrows or expands. Beliefs adapt to circumstances. On a long interstellar voyage, this process would unfold inside confinement. The founding culture might be recorded in archives, yet living culture would belong to those present, not to stored memory alone. This means the mission must expect transformation rather than assume static continuity. The challenge is not to freeze a society in its launch-era form. It is to allow culture to change without allowing that change to sever the knowledge and habits needed for survival. Conflict would be unavoidable because no human group remains free of disagreement for long. Personal tensions, disputes over status, grief, boredom, inequality of labor, questions of reproduction, and disagreement over mission priorities would all emerge sooner or later. On Earth, conflict can disperse across wider geography or be absorbed into larger institutions. In a spacecraft, there is no outside space into which trouble can simply move. Every serious conflict remains inside the habitat. This means systems of mediation, law, fairness, and accountability are not optional refinements. They are structural requirements for social endurance. The long time span also changes the moral character of the mission. A voyage lasting many generations would involve people living and dying without ever reaching the destination. Their work would sustain an outcome for others far in the future. Such a society might find dignity in that continuity, yet the burden is real. The mission would depend on individuals accepting that their lives form part of a chain rather than a completed journey. That acceptance cannot be produced by engineering alone. It depends on meaning, education, trust, and a social order stable enough to persuade each generation that the change should continue. So the human barrier to another star is not only that bodies are vulnerable or machines are limited, it is that time transforms travel into inheritance. Once the crossing becomes longer than the lives of the founders, the ship must contain a functioning society rather than a temporary crew. It must teach, govern, reproduce, remember, adapt, and endure inside a closed world of finite size. Under those conditions, the mission is no longer just a feat of transportation. It is an experiment in whether human continuity itself can be made portable across the dark between stars. Inside a spacecraft on a long journey, the human body does not remain unchanged simply because it is protected from vacuum and cold. Life on Earth develops under steady gravity, a regular day and night cycle, a broad atmosphere, and a living world full of subtle sensory anchors. A deep space voyage removes most of those conditions. The crew still breathes, eats, sleeps, and works, but the body receives a different set of signals from the environment around it. Over time, the altered setting begins to reshape the body itself. The ship may preserve life, yet preservation is not the same as health. A journey to the nearest star would therefore demand not only a functioning habitat, but a way of keeping the human body from slowly drifting away from the state in which it evolved. One of the clearest changes appears in weightlessness or near weightlessness. On Earth, the skeleton and muscles constantly push against gravity. Standing, walking, lifting, turning, and even sitting upright all require the body to support its own weight. Bone responds to this load by renewing itself. Muscle responds by maintaining strength. In orbit, that steady demand weakens. When the body no longer has to hold itself up in the usual way, muscles used for posture and movement begin to shrink. This loss is called muscle atrophy, meaning the wasting away of tissue through disuse. The legs, hips, back, and other load-bearing muscles are especially vulnerable. Exercise can slow the decline, but slowing is not the same as fully preventing it. Bone changes in parallel. Bone is living tissue, constantly broken down and rebuilt. Under normal gravity, this balance helps preserve strength. In reduced gravity, the balance shifts. The body may remove mineral from bone faster than it replaces it. The result is gradual bone loss, especially in regions that on Earth carry much of the body's weight. This weakens the skeleton and releases extra calcium into the blood and urine, which can contribute to kidney stone risk. On short missions and on orbital stations, careful exercise and medical monitoring help manage these effects. On a far longer interstellar crossing, the concern grows more serious because decline has more time to accumulate. The body cannot be asked to endure years of reduced loading without consequence. The heart and blood circulation also adapt to the space environment, and those adaptations are not always helpful. In weightlessness, fluids shift upward because gravity no longer pulls as much blood and other fluid toward the lower body. Faces can appear fuller, legs somewhat reduced in volume, and the body may interpret this redistribution as excess fluid. It may respond by reducing overall fluid volume. Over time, the heart does not need to work against gravity in the same way it does on Earth, and cardiovascular conditioning can change. When a person returns to a stronger gravitational field after long exposure to weightlessness, standing and moving may become difficult because the body has lost some of its ability to manage blood distribution properly. For a mission to another star, this matters not only during the voyage but at arrival. A crew weakened by transit may reach its destination less capable of functioning when capability is needed most. The inner ear and balance system face their own strain. On Earth, balance depends on the coordination of eyes, muscles, joints, and fluid-filled structures in the inner ear that sense orientation and motion. In weightlessness, those signals no longer align in the familiar way. Early in a mission, this can cause disorientation, dizziness, or motion sickness. The body often adapts with time, but long adaptation creates another challenge. Once the nervous system has learned a new spatial logic, returning to gravity or entering a different level of gravity may require yet another difficult adjustment. A long interstellar voyage would ask the body to remain adaptable for very long periods, which is not the same as simply enduring one transition. Sleep and biological rhythm are also vulnerable. Human physiology follows cycles tied to light, darkness, activity, meals, and social routine. These cycles help regulate sleep, hormone release, body temperature, and cognitive performance. In a spacecraft far from Earth, the crew may live under entirely artificial lighting and carefully scheduled timekeeping. This can be managed, but it requires discipline. Poor lighting patterns, constant machinery noise, stress, and confinement can all disturb rest. Sleep loss then spreads into mood, concentration, reaction time, immune function, and physical recovery. A body already working to preserve muscle and bone cannot thrive without regular sleep. In a very long mission, sleep becomes not a private comfort but a foundation of operational safety. Nutrition must support all of these systems at once. Food has to provide energy, protein, vitamins, minerals, and other compounds in stable balance across years. Too little of one nutrient may worsen bone decline, impair immunity, slow healing, or weaken mental resilience. Too much of another may create long-term metabolic strain. Preserved food also changes with time. Taste can fade, texture can degrade, appetite may narrow under monotony. The result can be subtle deficiency even when enough calories remain available. A healthy body in deep space does not depend on fullness alone. It depends on sustained nutritional precision under difficult living conditions. Mental health cannot be separated from physical health in such confinement. Isolation, monotony, distance from Earth, restricted privacy, and unchanging surroundings can all shape the body through stress. Chronic stress influences sleep, appetite, hormone balance, immunity, and cardiovascular function. Mood and physiology are joined. A crew living for years inside a limited habitat must therefore preserve not only discipline, but emotional steadiness. This requires meaningful routine, supportive relationships, personal space where possible, and a living environment that does not reduce the senses to endless sameness. The body suffers when the mind remains under prolonged strain. Immune function may also shift in space. The human immune system depends on many interacting signals from the body and environment, and evidence from spaceflight suggests that its regulation can change under stress, altered gravity, disrupted sleep, and radiation exposure. A crewed starship would need to assume that infection, inflammation, healing, and resistance to disease may not behave exactly as they do on Earth. Medical care, therefore, becomes part of daily survival. The ship cannot rely on rapid evacuation, outside doctors, or frequent resupply of specialized medicines. It must carry enough knowledge, equipment, and adaptability to respond to bodies that may age and react differently under the conditions of deep space. Exercise becomes the main physical defense against decline, but exercise itself is demanding. Treadmills, resistance devices, cycling machines, and structured training all require space, time, power, maintenance, and motivation. The crew cannot treat exercise as optional recreation. It becomes a medical necessity repeated day after day, year after year. This means the ship must support it materially and culturally. The body remains strong only if the environment insists on strength. So the challenge of human travel to the nearest star is not limited to keeping people alive inside a sealed habitat. It is the harder task of keeping them physically functional, while the surrounding environment quietly teaches the body a different way of being. Muscles soften when gravity fades. Bone thins when loading falls. Blood and balance shift. Sleep wavers. Stress enters metabolism, and health becomes a continuous act of correction. A successful interstellar vessel would therefore need to do more than protect the crew from outer space. It would need to resist the slow inward drift of the human body away from the conditions that make it strong on Earth. At the deepest level of the journey, the final barrier is not the hull, the engine, or even the habitat. It is the cell. The cell is the smallest unit of living structure that still carries out the work of life. Muscles are built from cells. Bone is maintained by cells. The blood, the lining of the gut, the nervous system, the immune defenses, and the reproductive tissues all depend on cells that divide, specialize, repair damage, and cooperate across the body. A human being can therefore remain outwardly intact while inwardly accumulating change at this microscopic scale. On a long voyage to the nearest star, that accumulation becomes one of the deepest reasons the journey remains beyond present human reach. Each cell carries DNA, the long molecular record that guides growth, repair, and daily function. DNA is not static writing stored safely away from harm. It is a working structure constantly exposed to stress from ordinary metabolism, from chemical byproducts inside the body, and from the surrounding environment. Even on Earth, cells are always repairing broken strands, correcting copying errors, removing defective components, and deciding whether damaged cells should continue living or be eliminated. Life persists not because damage never occurs, but because repair usually keeps pace with damage well enough for the organism to remain healthy. This balance is delicate. A long interstellar voyage threatens to disturb it. Radiation is one of the clearest sources of such disturbance. Energetic particles passing through tissue can break DNA directly, or generate reactive molecules that damage it indirectly. A single strike does not always lead to disease. Cells possess repair systems, and many injuries are corrected successfully. But repair is not perfect. Some damage is misrepaired, some is left incomplete. Some altered cells continue to divide. Over time, this raises the chance of mutation, meaning a lasting change in the genetic code. A mutation may do nothing important. It may kill the cell, or it may change the regulation of growth in a way that contributes to cancer. The danger lies not in one dramatic event alone, but in the long arithmetic of repeated exposure over many years. This matters especially in tissues that renew themselves often. Blood-forming tissues, the lining of the digestive tract, and the skin depend on frequent cell division. Every division is an act of copying, and every act of copying carries a small chance of error even under ordinary conditions. Add chronic radiation, altered immunity, stress, and unusual living conditions, and the burden grows. The body can often tolerate some flawed cells without consequence. It cannot guarantee perfect control forever. A starship does not merely ask a body to endure danger. It asks the body to keep accurate biological bookkeeping across prolonged time, while the environment continues to create new errors. Aging enters here not as a single program, but as the slow result of accumulated wear. Proteins misfold, cellular waste products build up, repair becomes less efficient. Mitochondria, the structures that help cells release energy from food, may function less cleanly and produce more damaging byproducts. Stem cells, the reserve cells that replenish certain tissues, may lose vigor or respond less reliably. These are active areas of research, and the exact weight of each mechanism remains under study, yet the broad pattern is clear. Human biology does not remain indefinitely at full repair capacity. It changes with time. An interstellar mission lasting decades therefore does not operate on the biology of departure alone. It operates on bodies that are aging while under unusual strain. This creates a hard inner limit. A crew may begin healthy, carefully selected, and physically prepared. Years later, the same people may carry more DNA damage, thinner bone, reduced muscle, altered circulation, disrupted immune regulation, and a growing burden of cellular error. The ship may still function, the mission timeline may still proceed, but the biological margin narrows. Recovery from illness may slow, healing after injury may take longer, resistance to infection may weaken, cancer risk may rise. The body becomes less forgiving precisely while the mission remains remote from rescue and dependent on constant human performance. Reproduction brings another layer of difficulty for voyages lasting beyond one generation. Reproductive cells are also biological cells subject to damage. Radiation and long-term stress can affect fertility, pregnancy, development, and inherited risk. The biology of conception, gestation, birth, and childhood development under prolonged space conditions remains poorly understood because human experience in such conditions is extremely limited. Observations indicate that many concerns are plausible, but it remains uncertain how a truly long interstellar environment would influence reproduction across generations. This uncertainty alone is serious. A society cannot responsibly depend on multi-generational survival in a setting where its deepest biological processes remain insufficiently tested. Cancer is perhaps the most familiar name given to the failure of cellular control, yet it is only one expression of the deeper problem. The true issue is cumulative damage across systems that depend on precision. Neurons must preserve long-lived structure. Immune cells must recognize threat without attacking the body itself. Blood vessels must remain elastic and intact. The heart must keep coordinated rhythm. Repair cells must respond to injury without excessive scarring or inadequate closure. Every one of these functions rests on cellular machinery shaped by Earth conditions and finite time. Interstellar travel asks that machinery to remain dependable, while the voyage itself becomes a source of ongoing microscopic strain. Even perfect engineering outside the body cannot remove this inner limit entirely. The best shield may reduce radiation but not erase it. The best habitat may preserve sleep and nutrition but not restore Earth in full. The best exercise systems may slow bodily decline but not guarantee lifelong stability. Human biology can be supported, protected, and monitored, yet it is not infinitely correctable. The deeper the journey extends, the more the mission depends on the continued fidelity of living tissue, and living tissue is temporary by nature. It persists through repair, replacement, and adaptation, not through unchanging endurance. So the impossibility of a human trip to the nearest star, at least with present knowledge and present capability, is not contained in one obstacle alone. It settles finally into the body at its smallest living scale. The dark between stars is crossed only if cells continue to divide accurately. Proteins continue to fold properly. Nerves continue to signal. Blood continues to renew, and damaged tissue continues to heal. A spacecraft may carry air, water, shielding, and engines. It may preserve a fragile world inside metal. Yet the journey still depends on a deeper world inside flesh, where atoms, molecules, and cells must go on choosing life against cumulative error for the full length of the crossing. At that inner frontier, the nearest star remains distant not only in space, but in biology itself. The journey inward ends where the grandest ambition becomes quiet. A human voyage to the nearest star begins in the sky as distance, then deepens into emptiness, speed, mass, heat, dust, radiation, shielding, habitat, society, body, and finally the slow labour of living cells. At every layer, the same truth remains. The crossing is not denied by a single locked gate. It is denied by a chain of limits, each one resting inside the next. The farther the thought travels, the more the problem leaves the realm of romance and enters the patient language of nature. The nearest star remains close on a galactic chart and remote in every human sense that matters. It is close enough to be named, measured, and watched. It is far enough that light itself requires years to arrive. Between here and there lies not only darkness, but a demand for speed beyond present engines, protection beyond present spacecraft, endurance beyond present habitats, and biological resilience beyond what human life can yet promise. The barrier is therefore not simply technological. It is environmental, social, and cellular all at once. And yet the idea continues to endure in the human mind because the mind is drawn outward. It looks at a single point of light and imagines approach. It places hope in design, knowledge, patience, and time. For now, those hopes do not close the gulf. The nearest star remains a destination for instruments, equations, telescopes, and thought more than for living travellers. It waits across a distance that is physically real and biologically unforgiving. So the night sky returns to stillness. The stars remain where they seem to rest, though each is moving in its own long path. Earth remains inside the warm boundary of one ordinary star, and the nearest other sun continues to shine across the cold between worlds, visible, measurable, and still beyond the reach of the human body.